Have you ever wondered how gambling, which is a recreation and sometimes an addiction for an individual, can be a business for the casino?
6 easy, no field market out on 6.
Big-time business requires predictable revenues, even when it's based on games of chance. Individual gamblers may win or lose and can't predict whether a day at Atlantic City will turn a profit or a loss. But the casino is consistently profitable. It's a remarkable fact that the net result of many thousands of chance events can be known with near certainty. The casino doesn't gamble. It doesn't need to deal marked cards or fix the dice or weight the roulette wheel. It knows that for every dollar bet, in the long run, it will make its profit. Better to concentrate on free floor shows and inexpensive bus fares to attract gamblers. The more dollars bet, the more money made. Other businesses make their decisions based on the predictability of certain events that are repeated many times. A life insurance company, for instance, doesn't know which of its policyholders will die next year, but it can say with remarkable accuracy how many of them will die. And it sets its premiums accordingly, in just the same way as a casino sets its jackpots. Let's be precise here. A phenomenon is called random if individual outcomes are unpredictable, but the long-term pattern of many outcomes is predictable. Many phenomena of both natural and human design are random in this sense. The lifetimes of insurance buyers, like cloud formations and hair color, are examples of randomness that occur in nature. But the odds or the payoffs on a game of dice are examples of carefully planned and produced randomness. Now, the dice used at a casino have their holes or pips carefully drilled and filled in with a material that's of the same density as the plastic that makes up the rest of the dice. This is done in order to ensure that the sixth side, say, isn't any lighter than the opposite side, which only has one pip. And once this is done, each of the sides is equally likely to land upwards. This is an example of a human design to ensure randomness. Now, deliberately planned or produced randomness is an idea that we saw before when we looked at collecting data. In selecting a sample or designing an experiment, statisticians take care to build in randomness with the mathematical benefits that we've already seen. The mathematics of chance, the mathematical description of randomness, is called the theory of probability. And we can use the theory of probability to describe patterns of truly chance events. Suppose I toss this coin in the air. Will it land heads or tails? Well, neither you nor I can say. But what we can say is that each outcome is equally likely. And what we mean by that is if forced to bet, we'd be willing to accept even odds. Now, while a definition of probability based on personal intuition may seem sensible, what we're after here is a meaning based on observation. Try tossing a coin not once, but 10,000 times. Well, I got up to about 100 times, but that's an experiment that takes lots of time and lots of patience. While he was interned in Germany during World War II, the British mathematician John Kerridge had plenty of both. And in fact, he did toss a coin a full 10,000 times. Here are his results. The first 10 tosses gave 4 heads, a proportion of 0.4. The proportion of heads increased to 0.5 after 20 tosses, and to 0.57 after 30 tosses. In a small number of tosses, the proportion of heads and tails fluctuates. It's still essentially unpredictable. But many tosses result in a smoothing effect. A proportion of 0.507, 50.7% heads, resulted after Kerridge threw the coin 5,000 times and resulted again after 10,000 trials. The proportion of any outcome settles down to a fixed number after many trials. The resulting number describes the probability of that outcome occurring in any given trial. Now, a probability of 0.507 in the Kerridge example means that heads are slightly more likely than tails to come up. You might think that this implies that Kerrich's coin was weighted or biased, because you'd expect things to come out pretty close to even with that many tosses. But in fact, there's some natural variability involved here, something we're going to look into a little bit later. And a difference of 70 out of 10,000 falls within acceptable limits. So we can't really say whether Kerrich's coin was fair or not. Now, the mathematician's first task in trying to calculate probabilities is to list all of the possible outcomes. Now, that list can be very short or very long. In the case of a coin, there's really only two things on the list, either heads or tails. In the case of two dice, there are 11 possible outcomes, all the way from snake eyes through 3, 4, 5, 6, all the way up to 12 for boxcars. Now, I can't say what any one roll of these dice will bring, but what I can say is that the number that comes up is going to be one of the ones on my list. The next step is to assign a probability to each one. But how do we make that assignment? Well, there are more ways to throw a 7 than there are to throw a 12. I mean, you can throw a 7 with a 5 and a 2, or a 4 and a 3. You can only throw a 12 one way. So it makes sense that the probability of the outcome 7 is going to be greater than the probability of the outcome 12. But just which number to assign is still a problem. Now, fortunately, there are two laws in the theory of probability which can help us with this problem. The first law says that the probability of any outcome on our list, say throwing a 7, is a number between 0 and 1. And the second law says that the sum of the probabilities for all of the outcomes is equal to 1. The first statement simply says that over the long run, each outcome never occurs, its probability of happening is 0, always occurs, its probability of happening is 1, or, and this is the case we're usually interested in, the outcome sometimes occurs. Its probability is between 0 and 1. The second property holds because since some outcome always occurs, the sum of all the probabilities of all the outcomes equals 1. It's important to understand what the probability of an event occurring does and does not mean. Probability is an expression of the likelihood of an event. It doesn't say what actually will happen. In order to find that out, you have to try it. So it's perfectly possible, for example, for a fair coin to land heads 10 times in a row. Probability only says what we expect to happen in the long run. Now, that's a key idea which we're going to come back to. Let's take the dice again, or rather one die. We believe that each side is equally likely to land upwards. So a plausible probability distribution is 1/6 for each of the 6 sides, with the sum of all 6 probabilities equaling 1. This probability doesn't describe all dice, only properly balanced ones. Here are some dice before their pips have been filled in. And here's one that's loaded. Its holes have been weighted unevenly. Now, the 2 side is lighter, so it's got a greater chance of landing upwards. Here's the result of some experiments with a loaded die like this. You'll see that the probabilities are no longer equal. Both probability distributions we've shown are legitimate, even if the dice aren't. Surprisingly, sampling is a lot like gambling. Well, maybe it's not so surprising when you recognize the fact that the link is randomness, the deliberate use of chance. So let's look back at that collection of light and dark beads that we saw earlier. The first time I scooped out 50 beads, I finished up with 12 dark ones, 24%. The second time, I drew out 8 dark beads, 16%. What if I take another sample of these beads now? Let's see. This time I got 7 dark beads. That's 14%. Now, this variability is the same sampling variability that we saw earlier when we were looking at surveys. But this time, I can use the laws of probability to describe it precisely. Now, I could keep taking random samples of these beads and writing down what percentage were dark. And each time, I'd get a number between 0 and 50, between 0 and 100%. So 0 to 50 is my list of all possible outcomes. But what probabilities do I assign to each outcome? Well, earlier, I took 200 samples of these beads. And on 32 occasions, I got 20% dark beads. So I could estimate that the probability of 20% dark beads is 32 over 200, or 0.16. Now 14 beads, or 28%, came up 14 times, so I could assign a probability of 14 over 200, or 0.07. Now I can plot these results on a histogram. The height of each bar represents the probability of the event described by the bar. But to explore this histogram further, we need some correct terminology. The number that I generated from my random sampling, the number of dark beads in a scoop, is known as a statistic, and the scoopful is called a sample. Now on the histogram, I assign probabilities to each of the outcomes. What I've done is to describe the sampling distribution of the statistic. What can the histogram tell me? Well, the sample proportions range from 6% to 38%. In the more precise language we're adopting, that means the sampling variability is quite large. Also, the histogram is fairly symmetric. We could put a rough axis through the bar that represents 10 beads, the 20% bar, which is also the outcome that occurred most often. But there's so much sampling variability that I wouldn't want to rely on a single sample to tell me how many dark beads there are in the container. So let's see what happens when I take 1,500 beads in each of my 200 samples. Of course, I couldn't find a bowl large enough for the millions of beads I would need, so I've let a computer simulate the results for me. This histogram is different from the first. The overall shape is narrower and taller. It's narrower because the sampling variability is greatly reduced. All 200 outcomes this time fall into a much smaller range. And if we add up the probabilities near the center, we find there's a probability of 0.93 that any sample will fall between about 18 and 22%. That means I can rely much more comfortably on the results of a single sample. And since I gave the computer its instructions, I know that the actual proportion is 20%, the same proportion of dark beads that I put in this box earlier. Look at the shape of both histograms. I can smooth them out by drawing curves across the tops of the bars. We now have two nice bell-shaped curves belonging to the family of so-called normal curves. We've seen shapes like this before, and you'll remember we identified the median, the point half the outcomes fall above and half below, and the spread. These two measures aren't usually enough to figure out the shape of a distribution of data, except when the distribution yields a curve like these. Normal distributions have the special property of being completely specified once the median and the spread are measured. Another property of normal curves is that the median falls in the same place as the mean. Now, the mean is the average outcome. On this normal curve, the median and the mean are identical, while here on this other curve, the median or middle data point is here, while the mean or average is here. The mean price of a new home in 1982 was $83,000. That's the average price. But the median price was only $69,000. As you can see, the distribution is not normal. By definition, half the homes cost more than $69,000 and half cost less. But some of the homes that cost more cost a lot more, so that the average or mean is higher than the median. Here's the distribution of heights of American women ages 18 to 24. You'll recognize from the shape of the curve that this distribution is normal. The mean height, 64 inches, is also the median height. Last time we also marked the quartiles, the middle 50% of the distribution. We can do this for curves as well. This gives us an indication of the spread of the curve without the extremes. For a population of American women, the quartiles fall at 62.3 and 65.7 inches. Notice that the quartiles are each 1.7 inches from the mean or median of 64 inches. This kind of symmetry is also characteristic of normal curves. In fact, for normal curves like these, there's a single measure of spread that, taken together with the mean, determines all of the percentiles at once. This single measure is called the standard deviation. A nice way to find the standard deviation is to run your pencil along the curve and look for the point where the curve changes from coming downward more steeply to coming downward more gently. Or another way to think of it is the point where the curve changes from coming downward into itself to coming downward away from itself. And of course, there's another one on the other side, too. There's another very useful property of normal curves. Let's take all of the outcomes that fall within one standard deviation on either side of the mean and measure them by volume, say. You'll see the probability of an outcome falling within one standard deviation of the mean is 0.68, about 2/3. Now, the point on the curve that's twice as far from the mean as one standard deviation is, believe it or not, 2 standard deviations. If we now pour out the curve that falls within 2 standard deviations of the mean, this time we have a probability of 0.95. Finally, here are the points measuring 3 standard deviations from the mean. And the probability now of falling within these limits is 0.997, almost 1. It's the property of all normal curves that the probability of falling within 1 standard deviation on either side of the mean is 0.68, within 2 standard deviations, 0.95, and 3 standard deviations, 0.997. That's a useful set of numbers to remember. 68, 95, 99.7. With these numbers, you can quickly derive useful information about any normal distribution. For instance, remember that the heights of American women between the ages of 18 and 24 are roughly normally distributed with a mean of 64 inches. So if I tell you that the standard deviation of this distribution is 2.5 inches, you can immediately tell me that about 68% of women are between 61.5 and 66.5 inches tall. 95% are between 59 and 69 inches. And almost all women, 99.7%, have heights between 56.5 and 71.5 inches. Very, very few women are 6 feet tall or over. Much of the importance of normal distributions comes from a key concept in probability theory, known as the central limit theorem. The central limit theorem says that the distribution of any random phenomenon tends to be normal if we average over a large number of repetitions. Now, that's a strikingly powerful notion. It means that we can analyze and predict many genuinely chance and haphazard events if we simply look at a large enough number of observations. We've seen this already with our bead scooping. Remember that each sample was a random selection, but when we looked at 200 observations, the results formed a normal distribution. And that means, in turn, that the tools we're developing apply to a very wide range of events, including the casino's games of chance, like roulette or dice. We also saw that sampling with 1,500 beads gave a distribution with much less spread. This is another implication of the central limit theorem, which says that spread decreases as the number of things you're averaging over increases. But hang on to that for later. Right now, let's apply the central limit theorem to one of the casino's simplest wagers, red or black in roulette. We have the chance to study this thanks to the help of this school for casino croupiers. David Britton's an instructor here. David, how about a quick introduction to the basics of roulette?
Sure. An American roulette wheel has 38 slots, of which 18 are black, 18 red, and 2 green. When the wheel is spun, the ball is equally likely to come to rest in any of the slots. A bet of $1 on red will pay off an additional $1 if the ball lands in a red slot. Otherwise, you lose. Actually, there are a lot of possible bets. Any one number, groups of numbers, and odd or even, as well as red or black. But if you bet on red or black, these 2 green slots, 0 and 00, belong to the house. Gamblers collect when red or black comes up, depending on their wager, while the house takes everything when the ball lands in a green slot. But the action really starts when I spin the ball. Place your bets, please.
Well, let's bet on red. Okay, I've taken the plunge. Now, while the ball's still spinning around, let's think about the possibilities. There are only 2 outcomes. I win or I lose. But now I can assign probabilities and figure out my expected value or return. Okay, let's say I play all evening, placing 50 bets. At the end of the night, I can figure out my actual average winnings per bet. It's simply my net gain or loss divided by 50. That gives me an average outcome per bet based on my experience. If I win 25 times and I lose 25 times, then my net is 0, and so is my average winnings per bet. If I get lucky and I win 30 and lose 20, then my net take is 10 bucks. Over 50 bets, that's an average winnings of 20 cents per bet. Now, at great personal sacrifice, let's suppose that I drag myself into the casino night after night, putting up with the free drinks and the excitement of the crowd, just to keep track of my average winnings. And just as with sampling the beads, my average winnings per bet form a histogram, which can be fitted with a normal distribution.
From the curve, you see that my average outcome fell between 47 cents lost and 37 cents won. The mean of the curve is a loss of 5 cents. But I didn't really have to go to all that trouble, because there's a way to calculate what my expected return should be. After all,
the probability of my winning $1 is 18 out of 38. The probability of losing is 20 out of 38, the 18 blacks and the 2 greens.
For one bet, my expected value is $1 times 18 of 38 chances, minus $1 times 20 of 38 chances for losing, which works out to an expected loss of 5.3 cents on each dollar bet.
What this is all for is estimating probabilities. In this case, I'm interested in predicting what I can expect on a typical evening of 50 bets. But in order to make that prediction, I have to finish analyzing this normal distribution. That means determining its spread or standard deviation.
We can trace the point where the direction of the curve changes. If we drop a line to the horizontal axis, we can read off the standard deviation as approximately 14 cents. There's another way we can determine it. The spread of this curve is about 84 cents. That range includes 99+% of my outcomes. By the 68, 95, 99.7 rule, I can conclude that this spread spans 3 standard deviations on each side of the mean. The standard deviation is therefore 1/6 of 0.84, or about 14/100ths.
Okay, what does this tell me? It's 99.7% sure that my winnings will fall within this range.
So after 50 bets, here are the results. You can think of these as extremes. I may win as much as $18.50, or I may lose as much as $23.50.
So if my losses are greater than my winnings, what am I doing here? Not so fast. Those figures are the most likely range of outcome after 50 bets. What's so exciting about gambling is that your outcome for a night of 50 bets is genuinely uncertain. You really can make some big winnings. That's all a matter of luck, and perhaps a good sense to know when to quit.
The casino, however, is in a different position. The house bets with all of its customers, as many as 100,000 individual bets on red or black in a single week. Now, the distribution of average customer winnings on 100,000 bets is very close to normal, and the mean is still minus 0.053.
But now recall the other feature of the central limit theorem that I mentioned earlier. The spread of a distribution decreases as we average over more and more repetitions. In fact, the central limit theorem is more specific than that. It states the spread of a distribution decreases with the square root of the number of bets that we're averaging over.
Watch what happens as the number of bets gets larger. Because the square root of 100,000 is much bigger than the square root of 50, the spread is much smaller. The standard deviation is not 14/100ths, but only 3/1000ths, much, much narrower.
Still following the 99.7 rule, the casino is nearly certain to take in an average that falls within 3 standard deviations either side of the mean. Now stay with me through these numbers, because the result's pretty interesting.
Because the casino covers so many bets, the standard deviation of the average winnings per bet becomes very narrow. And because the mean is negative, the entire range that includes almost all outcomes turns out to be negative. So the gambler's losses and the casino's winnings are almost certain to average between 4.4 and 6.2 cents for every bet that's made.
In other words,
The gamblers who collectively place those 100,000 bets will lose money. And we're now in a position to estimate the probable range of their losses.
The gamblers are almost certain to lose, and the casino is almost certain to take in between $4,400 and $6,200 on those 100,000 bets. What's more, we've seen from the central limit theorem that the more bets that are made, the narrower the range of possible outcomes.
And that's how a casino can operate gambling as a business. The more money that's bet, the more exactly the casino can predict its profits.
So what does this all add up to? With the casino examples under our belt, we can now look at the big picture. Many random events form a pattern when we average their outcomes over the long run. And according to the central limit theorem, that pattern takes the shape of a normal distribution. Normal distributions are completely determined if we know the mean or the median and the standard deviation. And using the mathematics of normal distributions, we can make remarkably accurate predictions about the pattern of many events.
Okay, let's flip for it. If it's heads, next time we'll talk about how to make reliable predictions and inferences. And if it's tails, I'm going to cover the windsurfing tournament in Hawaii. Okay, next time inferences.